Okay, next up, 1.5. This one's going to take a little bit longer, so gear up, but this is going to help us. This is the last time we have to do like all of these numbers, but it's a good primer for all of the stuff that we're going to have to know. So please know this stuff because this is really helpful. I think I go into it much more detail than your book does, but here we go. So there are two different types of numbers that we're going to have in chemistry. Okay, the types of numbers that we have are exact numbers and measured numbers. First of all, let's approach exact numbers. An exact number is anytime you count. So counted, anytime you count numbers. So there are 12 ducks, there are 14 mice. That's counted. Those are exact numbers. So they are not going to be we don't have to worry about significance, okay? Significant digits, and that's where we're headed with this. So if I say, oh, there are 12 ducks, no one is going to look at me and say, oh, there's only 10 because we can count them. They're physically right there. So anytime you counted numbers are exact numbers. They are not under the same rules of significant figures because they're counted. In addition to that is conversion factors. A conversion factor, which we're going to cover in part 6 in great detail, is anytime we do a conversion based on anytime we do a conversion. And so by this I mean, for example, a dozen. If I convert something from number of objects and I say, oh, there are half a dozen here. So if you go from 6 to a dozen, half a dozen, there are 6 in both cases. Because I use a conversion factor, it doesn't change what the number actually meant. So anytime we use a conversion factor, it's not going to matter. So 1 foot is equal to, or I should say 3 feet is equal to 1 yard. Anytime I use a conversion factor, convert from feet to yards, that is a well-established number. We don't have to worry about it. It's an exact number. So again, anytime we use an exact number, we don't have to worry about significant figures. Measured numbers are on the other hand, are the numbers that are the results of a measurement. So if I go and I measure the length of this coin, for example, in fact, what is the length of this coin? Write your number down. If I measure the length of this coin, that is a measured number. Okay, so there is a very specific number that is okay for this, and we're going to talk about that right now. So what is this? What is this, the measure of this coin? So as a scientist, it looks pretty obvious, but not necessarily. So looking at this coin right here, I can say for certain that 2 is the first number I want to put there. No one would argue with me there. If someone said, no, it's actually 1 point, no, that's not true. 2 is the number that I'm going to put in. All right. I'm going to say it's 2.5 centimeters. Okay. If you said 2.4, would you argue? 2.6, would you argue with that? Maybe a little bit, but if someone said 2.4, you could say, oh, I can see how it's a little bit below 2.6. Yeah, maybe if you're looking at it from a different angle, it might be a little it might be 2.6. Okay. The point of this is measured numbers have uncertainty. There are certain values that you're not certain of. Okay. So if you wrote down a measured number, if you measured this out to be 2.50, okay, if you measured this coin out to be 2.50, let me tell you why that's not really all that correct. Because we know this number, we are absolutely 100% certain about this. We are certain that that 2 is correct, right? No one's arguing that. No one could say that actually it's less than 2 or more than 2. So 2 is correct. That 5 is the value where we are a little bit uncertain. If someone said 2.4, someone said 2.6, you would let it go because this is our guess. And whenever you're measuring numbers, you always have a guess, right? I look at this area here, I blow this up and I say, oh, it's about 50% of the way to the 3. So if it's about 50% of the way, that's a 5 in that space, right? So by saying that's 2.5, I can totally trust that. This 0, though, If I was uncertain about the 5, I have no idea anything beyond that. So that one, that 0 there, I have no idea. I cannot say that exists. That 5, I'm uncertain about. Anything after the first uncertain number, you have no idea. So once you guess, everything beyond that is completely insignificant. So this number here is insignificant. If you added that 0 there, it's just wrong because we're not sure about the 5. We're absolutely not sure about anything beyond that. So the uncertainty itself is always going to be based on the measurement tool. Or the measurement that you're actually doing. So the measured value, there's always a little range. There's always a little range of uncertainty. Okay, so that little range of uncertainty is what allows us to have uncertainty in measurements, because the tool only measures to a specific point. We have to guess one and then we don't know the rest. So how we would actually write the length of this coin: 2.5 plus or minus 0.1. Notice that goes in the first uncertain digit, or the only uncertain digit. And then of course we always add our units. So 2.5 plus or minus 0.1 centimeters. That's the correct way to measure something. So significant digits is kind of what we're going to be looking at. Significant figures in measurement is always going to say, well, which one did I guess? What was the last one that I was allowed to have? So the measurement tool will give me some exact numbers. Okay, I know it's more than 2. I know it's less than 3. And that next one, I'm not sure. I'm going to have to guess on that one. So there are rules for significant figures, and these are important. Understanding these are important. It seems tedious, but as long as you understand them, as soon as you start to understand them, it makes it much, much easier. So a number is significant if it is not a 0. Any non-zeros are typically significant. Okay, so if we take a look, if I give you an example number, let's say 36.124. Every single one of those digits in that number is a non-zero, so it's not a 0. It is considered significant. So 1, 2, I'll do it this way. 1, 2, 3, 4, 5. There are 5 significant figures in that number. Easy enough. Every single one of those is significant. It's when you read, it's not when you're taking a measurement, you're not always going to take all of the numbers that you have, or when you're doing a calculation, you're not going to take all your numbers that you have. But if a measured number is written down, you have to assume that all of the numbers are significant. Okay. Any zeros in between numbers. By the way, what this is going to come down to is any placeholding zeros are unimportant. So if I have 303.1, let's say, again, 1, 2, 3, 4 significant figures. That 0 is in between 2 significant numbers. So we have 4 sig figs there. Okay. All right. Zeros at the end of a decimal. And this one gets people at times, but let's take a look. 1.200. If I'm writing a scientific paper and I add those zeros, why would I write them? Why would I write those if they were not significant? They are. So any zeros that continue on are significant. So 1.200, each of those is considered significant. We have 4 sig figs in that space. Okay. If I don't need the zeros, I'm not going to write out the zeros. Okay, next up. Any digit in the coefficient of a number written in scientific notation. All numbers in scientific notation, and we're going to cover scientific notation briefly, 6.02 times 10 to the 23rd. These numbers out here in front, each of those must be significant. That is 3 sig figs. Every number in a scientific notation has to be significant. If it's not significant, it doesn't belong in front. Okay. The next group, any place-holding zeros are considered insignificant or non-significant. Okay. So zeros before a small number. If you have to give me the place, if you have to 0.000410, for example, okay? All of these are considered, once you find your first significant figure, everything after that is going to be significant. So the 4 is the first significant. There are 2 others after it for a total of 3 significant figures total. All of these zeros are telling me are that where we are in terms of how small my number is, right? So that's the point of that little significant figure, the zeros out front. All right, last one or 2 actually, and this is the one that's a little bit weird, but kind of neat. So if I have 21,000, 21000, again, those zeros are just placeholding. They're telling me the size, the magnitude of that 21, that number. So I would say that there are 2 significant figures there. But here's the rub. As soon as I add 21,000, as soon as I add a decimal, that makes them all significant. So now there are 5. By adding that decimal, you're saying all of those zeros are important, and we have 5 significant figures now. It's a little bit weird, but it's how it goes. so yeah. So how many significant figures there? And I want you guys to round these. We're going to talk about rounding in class together. So round these. Okay, let's see if you can do it properly. By the way, I have to tell you what to round to, right? Because you're not sure. So whenever I tell you to round to something, or whenever you round, you always need to underline where you want to round. So you always underline the number that you're rounding to. Okay? So round to that number. Good. Yeah. All right. Actually, I'm going to add 1 to the end of this. I'm just going to put a 1 there. 0.50001. Okay, perfect. So around those, do that other stuff. And now I want you to measure these objects. All right, so come up with the values for these objects, and we're going to discuss it in class. Okay, so write out the measurements, and if you can, including uncertainty and units for these. Okay, all right. So again, based on the measurement tools that you have, so those 2 rulers are what you have to use. So let's talk about different types of data that we're going to get. So there are 3 different attributes to a data set: precision, accuracy, and trueness. You probably have never heard trueness before, but it is a thing. So precision. Precision is how well measurements again, we're talking about measurements, measured numbers. How well measurements compare to one another. So how well measurements compare to one another. So in this case, on this little thing to the right here, the precision is how well clumped they are. So if those numbers, those little blue dots are really well clumped, you're going to be very precise. If they're spread out, these seem a little more spread out. If they're spread out, it's not a very precise set of data. Okay. And then there's accuracy. Accuracy is how close the measurements are to the accepted or the true value. Okay, so in this case, these things are pretty far away from the red dot, which is the true value. So these are not as accurate either. So this data is not very precise. This data set is not very accurate. And then the trueness part of this is how well the mean of the data compares to the true value. Okay, so precision, accuracy, and trueness. We're probably going to look at precision and accuracy mostly. Precision, how well clumped together. Accuracy, how close to the true value. And then trueness is kind of another one that's kind of neat little trivia. So group A, group B, and group C. The true value, because we're talking about that coin, is 2.50. okay? 2.5. All right, so how is the precision? How is the accuracy? And how is the trueness for each of these groups? So go through these and we're going to talk about it in class: precision, accurate, or true. Okay. All right, good. So significant figures in calculation. So we took a look at significant figures. We talked about measured numbers. We calculated this coin. We said this was we said that the diameter of this, or the diameter of this is 2.5 centimeters. Okay. That is, 2.5 centimeters. So what's the radius of this coin? Well, we know that radius is equivalent to diameter divided by 2. So if I take the diameter of 2.5 centimeters divided by 2, my radius is equal to 1.25 centimeters. That's it. Plug it into the calculator, divide it by 2, and I have 1.25 centimeters. There's a problem with this, though, because up here we see I have 1 decimal place. Down here, I have 2 decimal places. So I measured the coin out to the 10th place, and then by dividing by 2, it's now out to the 100th place. How did I increase the ability to measure this thing? Because remember, I said 2.50. That was wrong. I can't measure out to that 100th space because my ruler doesn't let me. So how, by just dividing by 2, can I measure out there? And the answer is you can't. So we have to take into account significant figures when we're doing a measurement. So the real radius of this, by the way, is 1.3 centimeters. And let's take a look at these rules. And these are, again, significant figures in calculation. I kind of like these. They're really nice little nice little maths to do. So there are 4 rules, or there are 3 rules for significant figures. Well, 4 rules for significant figures in calculations. So first and foremost, anytime you add or subtract 2 measured numbers, again, this is all about measured numbers, we are always going to round to the fewest decimal places. So it's easy to look at an example. So here I've got 22.3, 52.02, equals 74.32. So together I have 74.32. I guess I just did that. All right. 74.32. Well, if we take a look at this calculation, we notice that, so again, addition, abstraction, fewest number of decimal places. So this is addition. We have 74.32. This number has 1 decimal. This number has 2 decimals. We can't be more accurate than our least accurate measurement. When I was measuring these things, the first number with 1 decimal place was the least accurate measurement. That means that my answer has to be rounded to the least accurate measurement according to the rules. So the answer for this is actually 74.3 meters. Okay, solve the next one. For multiplication and division, we are no longer interested in the number of decimal places. Instead, for multiplication and division, I'm interested in the fewest number of sig figs. So when we look at this number below here, 23.5 meters times 0.023, 0.025 meters gives me 0.5875. So first thing I always want to do is I want to do the calculation. I want to write out all of the numbers. Okay. So, and of course, I also want to add in the units, meters squared. Now, how many sig figs do these things have? Well, this number has 3 sig figs. This number has 2 sig figs. That means my answer is limited by the least accurate measurement. The second number has 2 sig figs, so we are limited to 2 sig figs. Round to that, the actual answer is 0.59 meters squared. Okay, We're always limited by the number of sig figs when it comes to multiplication and division. Those are the ones that those are the most important ones to remember. These next two are ones that people never remember. In fact, I asked one of the physics guys if he remembered, and they didn't. And it's really important to know. So here we go. For roots, anytime you take the root of something, you're always going to add one sig fig. Remember, again, this number right here is measured. So again, you don't do this when you're just doing some math. You're going to use all those numbers like, square root of 9. You're not going to just skip it. Only when you have measured numbers that you're actually doing calculations on. So square root of 54.34. All right, first thing you do is you plug it in your calculator and you find it's 7.371566997.5 and on. So often I see this in labs. You guys just write out all of the numbers. We have to stop at some point, okay? So for roots, we're going to add one more number. So what you're going to notice is we have how many sig figs? So this thing has 4 sig figs. So 4 sig figs plus the 1 that we're going to add, because that's how we do roots. Give me 5 sig figs. 1, 2, 3, 4, 5. That means I'm going to underline that 5. My number is 7.3716. That, and there's no unit for this one. That's the correct answer for a root. Okay, last one. For powers, we do the opposite of what we do for roots. We're going to take one less. Okay, so 9.02, again, that's a measured number that I'm squaring. I end up with 81.3604. In my calculator, my original number has 3 sig figs minus the 1. I should have 2 sig figs when I'm finished. So 1, 2. We're going to underline that 1 there. We end up with a value of 81. There's no unit, but that's where we're at. Okay, so only measured numbers do you have to do the sig fig thing, not exact numbers. That's why I was harping at it at the very beginning. Okay, good. Okay, so next up, when we're doing calculations, it changes a little bit more. So I have this in scientific notation. We're close to done. So when we're doing calculations, it changes a little bit more. So first of all, we're going to solve the problem by, again, we're going to follow the order of operations. We're going to keep track of the sig figs, and then at the very end, we're going to round. So we're never going to round until we get to the very end. So following order of operations. So if we follow the order of operations, if you remember, it's PEMDAS, right? PEMDAS, where the P is parentheses, the E is exponents. By the way, I'm also, because it's the same thing as exponents, I'm going to put roots in there, right? The square root of 2 is the same thing as raising it to 1/2. So exponents and roots. Multiply, divide, and then add and subtract. So we're always going to follow that. And again, the final thing from left to right. So we're always going to do these from left to right. So if I have 2 additions, I'm always going to do the left addition before I do the right addition. Okay. We're going to keep track of sig figs. And we're going to do this by underlining where we would have rounded. And then finally, we're never going to round until the very end. So I'm always going to keep all of the numbers until I get to the very end. So this is the math problem that I have here. So go ahead and try to solve this first if you want to, and then go pause this and record this, or pause this and try it out and see if we get the same answer. All right. So first thing that we do, first order of operations, is we're going to do the parentheses. So with that said, I'm going to rewrite the top. And I'm going to do what's in parentheses. And if we do what's in parentheses, we end up with 1.332 on our calculator. Great. Where would I have rounded? So that's always the question. Where would I have rounded? So if we were doing this problem, we're subtracting, go back to your rules. What do we find out? Number of decimal places. So this one has 3 decimals. This one has 1 decimal. My answer should have 1 decimal. So when I go to my answer here, I would have rounded right there. Not going to round yet. I'm going to use all those. In fact, when I do the calculations, I am going to use that number, that whole 1.332 number. We would have rounded there. Good. All right. Next up. So we always underline where we're going to round. What's next? We're going to do the top, right? Before we do the division, we'll do that multiplication up top. So 3.12 times 1.45562, you end up with 4.5415 344, all divided by that 1.332. And of course, I would have rounded to that 3, so I'm going to continue to follow where I would have rounded. All right, back to the top up here. When we multiply, we're interested in the number of sig figs. So this number here has 3 sig figs. This number here has 6 sig figs. The one with the least is the 3. So that means when I'm looking here, I would have rounded to the 3rd sig fig. We still have one more operation to do. Notice that I have not rounded yet. Now, when I plug this into my calculator, I'm going to use all of that. So 4.5415344 divided by 1.332, and we end up with a value of 3.409560 360, and it continues to repeat at that point. Okay. Now what? Well, we divided, and because we divided, let's finally look at these numbers, and I'll use a different color for this. So this would have been the number, although we did use all of the digits. This would have been the number that we did, and this would have been the number that we had. Those are as accurate as we can get. And we divided, so we're interested in the number. This has 3 sig figs. This one has 2 sig figs. That means our answer gets rounded to 2 sig figs. And we're done with all of our calculations. Now we can actually do the math. We end up with 3.4. That's the correct answer. Okay, that's it. That's how you do those things. We're going to do a bunch more problems in class, but do this one to start, and we're going to take a look at it. Okay, good. And the final thing, scientific notation. Scientific notation, we use this to simplify numbers. No one wants to write 6.026. No one's going to write all of those zeros now. Okay, so scientific notation, we can certainly talk about this if you guys are unsure about it, but we have the power, and we're going to go through these just a little bit each. We have the the exponent, we have the power that we raise things to, and we have the coefficient out front. So let's take a look at these things individually. So the coefficient, this is always a number between 1 and 10. Okay, and they are always all significant. Okay, all of those numbers are always significant. 6.02, there are 3 significant figures in this scientific notation. Okay, the power, because we use a base 10 power in our number system, this is our power. Yeah, we always use that. And then finally, the last little bit, the exponent. It tells you how many orders of magnitude, and that's important. Orders of magnitude. Anytime I say that, remember I'm multiplying by 10 or or 100 or dividing by it. orders of magnitude. So anytime you talk about the magnitude of a number, this is what you're talking about. Okay. Remember, when it comes to orders of magnitude, a positive exponent means it is a number greater than 10. Okay, so it's greater than the coefficient, and we are moving the decimal to the right. If it's a negative exponent, it is less than the coefficient, or it's less than 1, and we move the decimal to the left. We use scientific notation to represent small or very tiny numbers, right? So the Earth is 93 million miles from the sun. Convert that to scientific notation. I would never report that the length of a carbon-hydrogen bond is 0.0000000000109 meters, right? I would never do that, because you could just use scientific notation to help your readers, okay? And then finally, the width of an HIV virus is 9 times 10 to the negative 7th. Convert that to scientific notation. Good. All right. That's it. And yeah, so we'll move on. We're going to do the next part in class, because I want to go through a bunch of conversions together, because it's really important stuff to know.